Hi everybody, happy snow day, and here is your first video on error. There's going to be a couple or maybe a few videos here talking about different kinds of error. Now on the AP exam, almost every series free response has one part of it on error. There's two types of errors that you need to know for the AP exam. There's something called Lagrange error and alternating series error. We're going to talk about an intro to error. I'll do a proof of Lagrange error. I'll show you how to use it in the videos. Next time I see you in class, we'll talk about alternating series and practice them, okay? So let's talk about an introduction to error and build it off of what we did in class last week. Let's say I have the function e to the x, and I write down the Taylor series for it, which is, where's my cursor? Which is right here. So this is something we already know. And let's say that I truncate it to be p sub 3. So I go up to the third degree. So this is my polynomial approximation for e to the x up to the third derivative, the third exponent. Now I want to use my polynomial approximation to approximate something. So let's approximate f of 1/2. Now keep in mind f of 1/2 is really e to the 1/2 because f is e to the x. So I'm going to plug 1/2 into my truncated polynomial and I'm going to get an approximation. So I show the work right here. F of 1/2 is approximately equal to p sub 3 of 1/2. When you do your common denominator work, you get this value right here. So this is equal to p sub 3 of 1/2. In class, we talked a little bit about error, just a very brief introduction. And we decided, or you've seen this before in science classes, that error is equal to actual minus predicted. You do the absolute value of it so you get the magnitude, because sometimes one is bigger than the other. You just want the number. The sign doesn't matter. So the difference between your function value and your polynomial is your error. So I'm going to write that out here. So f of x minus p of x. F of x is actual. P of x is your predicted polynomial value. In this case, we did it at 1/2. So I'm plugging in 1/2. F of x, which is f of 1/2, is e to the 1/2. P of 1/2 was what I found above here. And in this case, I can find what the error actually is. This is the true error, 0.002888. This is really small. I only went to the third degree. So I only have 4 terms here, third degree, and my error is tiny. Now, sometimes you're not going to be able to do this to find what the actual error is. So then we talked about another way to think about error. The reason that your polynomial approximation, which is this, is not the actual value of f of 1/2 is because you cut off all of these guys, starting at x to the 4th and going on. If you hadn't truncated it and if you'd included all these, it would have been exact. But because you chopped it right there and you got rid of all these guys, that's why it's not the same. So this right here, all those terms added up is the error. It's another way of thinking about the error. It's all the remaining terms. So what I did is I wrote out the remaining terms. Now we're going to be talking about this idea of n plus 1 a lot here. Notice that p sub 3 went up to the third degree, which is found using the third derivative. The coefficient is found with the third derivative. Error starts at the next one, which would be n plus 1, the fourth. We're going to be using that idea for pretty much all the error topics. So since p sub 3 stopped at the third degree, the error starts at the fourth degree or the fourth derivative, going onwards. So the rest of the terms here that we didn't use, that's the error. So there's different ways of calling error depending on what book or video you watch. You can call it r of x for remainder or the remaining terms. You can call it e of x for error. If you did statistics, you don't want to mess this up with expected value, so that's why some people use r instead. But you're going to see both. I'll probably switch back and forth here. And let's see here. Let's get a graph going. Let's be a little more general here, and let's just draw some random function f of x. Now what we're going to assume here is that we wrote a polynomial approximation and we're going to sketch it. And let's say we did it to the nth term, the nth power. Now keep in mind that whatever the power is, that's how many derivatives you took. So if you stopped at p sub 3, it's to the third power of x. That means you did up to the third derivative. So let's go stop at p sub n. We want to keep it real general. That means we went up to x to the n, and that means we took the nth derivative. And let's center it at a. So this is where it's centered at. Oh, side note, make sure that you wrote all this stuff down here. And again, make sure you're writing all the things down. You're not skipping anything. So if you have to go back and add anything, do that. So back to here. I am going to do a quick sketch of what the polynomial might look like. Remember, the black one is the actual function. The red one, since it's centered at A, when you're real close to A, they're going to be pretty much the same. And as you get further and further away, it's going to slowly get further and further away as well. So this might look something like that. And now what I want to do is I'm going to pick another value, let's say B, and I want to find the error at B. If you just look at it, the error at B is this distance right here, which in this case is the actual function's value at B minus the polynomial's function at B. So the error at B is the function's value at B minus our predicted value at B. Now you could do subscripts of n to let yourself know that you went up to the nth degree and nth derivative here, but you can just stop and assume that you know it's at the n. One thing to realize is if you're at A, so at A, there's no error because, so the error, I'm going to use E here for error, okay? The error at A would be the function's value at A minus the polynomial's value at A. That's 0 because the function's value at A is equal to the polynomial's value at A. And you can see there's no difference in the height. Now let's say I took a derivative here, and let's say I want the derivative of the error at A. Well, that would be the derivative of f at A minus the derivative of p at A. One thing I want you to remember is the last video that you watched last week, what we did to find a Taylor polynomial, this was the longer way. It's where you wrote it like this instead of writing it like this. This is the quicker way to get a Taylor series from scratch. The slightly longer way was to do it like this with the c's. And what we did is we took derivative after derivative, and every time you took your polynomial value and you set it equal to your function value. Then you did another derivative. You took your polynomial value and you set it equal to your function's value. And those values were equal to each other. Poly equaled function up to the derivative that corresponded with how far you were going with the polynomial. So let's say you did p sub 4. That means you had to go up to the fourth derivative. So up to the fourth derivative, the function's value was equal to the polynomial value. After the fourth derivative, once you got to the fifth derivative, they weren't equal anymore because that would be where they start to spread apart here. So if I go up to n, let's say, n something, 3 or more, that would mean that the first derivative of the function is still equal to the first derivative of the polynomial. So f prime of a is equal to p prime of a. And you can keep going here. The second derivative would be equal to third derivative. Now again, I don't know what n is, but I could go all the way up to n. So the derivative, the nth derivative of the error at a would be the nth derivative of f of a minus the nth derivative, of the polynomial at a. And that would equal 0 again, because up to that nth derivative, you can still set them equal to each other. Minus p, equals p n of a. Now, once you get past n, you can't exactly set them equal to one another. Let's summarize what we just said above. There are many useful things about polynomials, but in terms of Taylor polynomial series, one of the useful things about it is that you can approximate f of x with an nth degree polynomial, p sub n of x, and up to and including the degree of the polynomial, so in this case n, when you evaluate the derivatives of your polynomial at a, they're going to be the same as the derivatives of the function at a. So the polynomial value will equal the function value up to n. Our main goal here is going to be to bound the error. You want less error rather than more, so you're going to try and bound it on a certain interval. Let's continue right here. So jot that down, pause the video if you need to. And then let's go ahead and see what happens if we go beyond n. So e to the n plus 1 at a. The n plus first derivative of the error function at a, that would be f n plus 1 at a minus p n plus 1 at a. If I take an n plus first derivative of a polynomial of degree n, remember the degree of a polynomial is n. Maybe we should generalize this to x because the derivative at a value is just going to be a value. So I'll make that x here. What's going to happen if you have a polynomial of degree n and you take the n plus 1 derivative? Let's consider a polynomial x squared. That is degree 2. If you take the 2 plus first derivative, that'd be the third derivative. Well, the first derivative is 2x. The second derivative is 2. The third derivative, the n plus first derivative, is 0. That's going to be true for any polynomial. Of degree n, the n plus first derivative is going to be 0. So that means my error function is equal to the function at the n plus first derivative at x. Now our goal here is going to be to bound the error. And we can put absolute value bars around it because I just want the polynomial. So this means here that I can find the error of my function or of my approximation with the n plus first derivative of the function. We're going to continue this, and this is actually going to come up again in a proof that we're going to do. So I'm going to do the proof in the next video because I would run over anyway, and the proof is going to use the mean value theorem. So get this down so far and then continue in the next video.